Thanks for the invitation to come here. This is a great program. Wish I could have stayed longer. Let's see, my co-authors, Catherine Wolfram, who's at Yale, and Cosmin from earlier. They're both a bit older than they look in these pictures, but still both young looking. Let's see. Yeah, so the sort of motivation is, counting tilings in general, as we all know, is a very difficult problem, and be hard for a finite region, even not, sort of undecidable if you want to decide whether your set of tiles tile the plane. Right, we have some finite set of some finite region. You have some maybe some set of tiles, and you want to know if those tiles can be fit into tile exactly. And of course, if you want to do stat mech, you want to do more than just tell it there is a tiling. You want to be able to count tilings, which seems kind of hopeless for general tiling sets. But the cases where we can do counting always have interesting and deep mathematics. So what we want to do is what I want to do today is to sort of talk about a variant of the tiling problem, which with in some sense easier counting. And that's called the multinomial tiling model. We invented this with Cosmin, a few years ago. It's not really very, difficult, as you will see. It's just a sort of different point of view on sort of a certain relaxation of the tiling problem. And it does have some features that we see in the usual, in our standard tiling models, like certain limit shapes and some conformal invariance sometimes, and sometimes not. And some interesting sort of long-range orders, even quasi-crystalline order, which I won't talk about today, but other sometimes happens. What it doesn't have, and there's some things it doesn't have, at least not that we haven't discovered yet. It doesn't have facets and so much connection with algebra. But here, let's just go with the definition. And feel free to interrupt, by the way, about it. The talk is not super long, so I'm happy to go slow and discuss any aspect here. Okay, so we're going to start on a graph, finite graph. Doesn't have to be planar, but my pictures will be mostly planar. G is a finite graph, and as a tile, I'm going to call a tile just a subset of the vertices. So it's a fairly general tiling model. T are the set of tiles, and rather than tiling G with the copies of the tiles, I'm gonna blow up G. That is, replace each vertex. Here's G down here. I'm gonna replace each vertex with n vertices, where n is some number. So let's call Gn the n-fold blowup, which means that just replace each vertex of the original graph with some number n sub v, or well, it could be constant n. Vertices lying over that vertex. And then each edge in the graph, if you want, gets replaced with a complete bipartite graph of the upstairs graph. Make sense? And we don't have to have, and n doesn't have to be constant. It can vary from vertex to vertex. Like here, n is 4 over this vertex, 3 over that vertex, and 4 over that vertex, and so on. So n is really, when I write boldface n, I mean the multi-vector, the vector of multiplicities, one for each vertex of the downstairs graph. And for this talk, we are going to take our tiles to be exactly the set of edges of G. That is, I'm thinking about each tile as a dimer, a single edge of the downstairs graph. But what I'm going to do is a tile. Oops, I'm going the wrong way. The goal is to, so the multinomial tiling model just says, instead of tiling the downstairs graph, we're going to tile the upstairs graph, Gn, with copies, lifts of the tiles T. So, somewhere I said that. So, for example, and for the rest of the talk, our tiles are just going to be dimers. And so, if your original G, the downstairs G is a square, and here the multiplicities are all 2, this is an example of a tiling of the the upstairs graph. And you can see that, so the pink edges it's just a dimer cover of the upstairs graph. I'm just interested in dimer covers of the blow up graph. But of course, rather than thinking about the blow up graph, I can project back down to the lower graph, and each edge here will project to an edge of the downstairs graph, which is a square with some multiplicity. And so when you project, if you take a dimer cover of the upstairs graph and you project down, see, you get what's called an n dimer cover. Suppose all the multiplicities are n, you get an n dimer cover, which means just a function on the edges, an integer valued function on the edges, non-negative integer, which sums to n at each vertex. So, for example, in this particular example, the graph is the downstairs graph is a square. All the multiplicities are 2, and there are sort of 3 configurations after you project from the dimer cover upstairs to the downstairs graph. You can either have multiplicity 2 on the 2 vertical edges, multiplicity 2 on the horizontal edges, or 1, 1, 1, 1. So these, in other language, these are called double dimer covers of the downstairs graph, but for a general n, they're called n dimer covers. And let me just read the slide. An n dimer cover is just a function on the edges to non-negative integers, such that around each vertex, the sum of the multiplicities adds up to n. Or, and if n varies from vertex to vertex, this is n sub v. However, this is not, our measure is not the same as a uniform measure on these configurations. It's the uniform measure on the dimer covers of the upstairs graph, but when you project, you don't get the uniform measure. You get a measure which is proportional to the product, to 1 over the product of the edge multiplicities. For example, if you think about how many upstairs dimer covers project to this one, how many are there? What?
Do what?
Well, over this vertex, there are 2 upstairs vertices, and you have to choose one of them to go that way and one of them to go up. So there's 2 choices per vertex. So there's 16 total, right? So this one has multiplicity 16. These guys have multiplicity 4 each. Okay. Did that make sense? Okay. Well, so there's a very simple weight formula, which sort of generating function for the set of total dimer covers. So let's let Z. Yeah, you can barely see this slide, but let's let Z boldface n be the number of dimer covers of the blow-up graph. Here I said tilings, but I mean dimer covers by the lifts of the. Well, in fact, this whole slide is true for the general multinomial tiling model. So, but in general, this theorem holds. But if you like, you can restrict to the dimer model. But it holds for general tiles. You have some tiles T1 through TK. You look at the number of tilings of the blow-up graph by those tiles, and we make a sort of exponential generating function out of these Z sub n's, the partition functions. And the theorem is that exponential generating function is has a very simple form. It's e to the p, where p is a certain multivariable polynomial. And well, okay, so sorry, I skipped ahead. X for each variable in the downstairs graph. For each vertex in the downstairs graph, let's have a variable xv, and we'll make this polynomial, multivariable polynomial, which has for a monomial for each tile, and the monomial is just the product of the variables at its vertices. That's called the tiling polynomial. And when you take e to the p, this is the exponential generating function for the desired quantities, the partition function of the number of tilings by those tiles. Right? It's a sort of multivariable exponential generating function here. So, you know, the right-hand side is very simple. And in principle, all you have to do is extract a particular coefficient from this, you know, power series e to the p to get the desired quantity. And of course, you know, it's a pretty formula, but it's not super useful as is because, you know, we know that this is hard to compute. If for example, boldface n is 1 at every vertex, then we're just computing the number of tilings with our fairly general set of tiles, and we shouldn't expect to have some, you know, magic way to compute that. So it's an NP hard problem. So even though the formula is very simple, really it's just recasting the hard problem in terms of, you know, extracting some coefficient from some big multivariable generating function. However, there is something you could do in this situation, which is to let n get large and use a saddle point method. And that's the basic idea. We're going to let the multiplicities all go to infinity at the same time here with some rates. Suppose that each vertex multiplicity goes to infinity is the form alpha v, a constant, times n as n goes to infinity. And then you can what you need to do to compute this partition function is you know, extract a coefficient from this e to the p, and you can use the saddle point method in this. This is exactly what the saddle point method was invented for, this kind of coefficient extraction. It's kind of straightforward because e to the p has all positive coefficients. Everything is sort of nicely convex. There's a unique, you know, critical point, and the saddle point method tells you that you need to solve this, you know, find the critical point of this functional, find the unique critical point for this functional. And so there's some equations that you need to solve. What do we need to do? We need to find the x values here. These x's were originally variables, but now we're looking for positive real x values which satisfy this equation. Here, p is our polynomial, alpha v's are our constants, telling us how quickly the n's are growing, and c is some constant. C is like n. So our asymptotic expansion now just comes down to solving this system of polynomial equations. And we're looking for a unique, well, there's some convexity, and so there's a unique critical point. So in principle, it's kind of an easy exercise to find this critical point because it's convex. It's a minimum of some convex function, and your computer can do that very quickly. But okay, so now what's going to happen is that, you know, this was all for a finite graph, and what we're interested in is sort of letting the system size get large. And so for a finite graph, we're looking for this, we have this sort of system of equations, or if you like, we're looking for a critical point of some multivariate function. In the limit of large system size, when we take a sort of a scaling limit of our graph, if our graph is approximating some region, some geometric region in Rn or Rd, then this multivariable critical point equation becomes a variational problem, or a functional on the, well, what was originally the vertices of the graph is now just going to be a sort of continuous function on our region. So it turns our saddle point problem into a variational problem, continuous variational problem. Does that make sense? Are we following? Okay, let's go back to the finite graph case just so we can see how it works in practice. First of all, for, you know, the easiest situation is where all the multiplicities are the same. So let's do that. At every vertex, all the multiplicities are just n, little n, some constant. And then the critical gauge equation from the previous slide here, up to scale, you could just set the right-hand side to be 1, some constant. And we might as well do that constant to be 1 because it's convenient. Then for the dimer model, this is the equation we need to solve. We need to find, we have our graph G, our downstairs graph. We're looking at, for a function on the vertices, such that at every vertex, the sum of the products of the adjacent variables adds up to 1. That is, at every vertex, the edge weight becomes the product of the adjacent vertex weights, and you want that sum to be 1. Right? And so it's in the Dimer language, we're looking for a certain gauge function that is a function on the vertices, such that the sum of the edge weights, where the new edge weights are just the product of the corresponding vertex weights, the sum of the edge weights around a vertex is 1. And if you do that, then in the multinomial model, remember our multinomial model is some Dimer model of this upstairs graph. When we project back down to the downstairs graph, the fraction of edges which project to a given direction will be this weight, this critical weight. So here it is in practice. So I just took a 2x3 graph. We start with just the adjacency matrix of the graph. This is the sort of bipartite adjacency matrix. So the rows are indexing the white vertices and the columns are indexing the black vertices. What we need to do is find a function on the white vertices. The x1, x2, and x3 are the values of the white vertices, and a function on the black vertices representing a diagonal matrix acting on the right. We want to find these x values such that when we multiply the adjacency matrix by this, I get a matrix whose row sums are 1 and whose column sums are 1. It's bistochastic. And if you do that, you find there's a unique solution for positive x's, and it's this one. It involves the golden ratio. Right, so that's the mantra here, is to make the adjacency matrix bistochastic by choosing an appropriate gauge. And so the claim is that if I take this multinomial model, if I over this graph, if I look at my blow-up graph where n is large, then the fraction of dimers which will at this vertex, the fraction of dimers which are vertical versus horizontal is square root of 5 minus 1 over 2. With high probability, it's kind of a law of large numbers result. Okay, so that's cool. But to do this, we have to solve some non-linear polynomial system of equations. It's kind of not obvious how to solve that. And if you do it on another graph like this one, here's some. I used my computer. My computer solved this on some other graphs like these two, and it's a little bit disappointing because they're algebraic. Of course, they're algebraic, but the sort of degree increases with the size of the graph. It looks kind of like a mess. Doesn't look like, even if you take some, as the graph gets larger, it doesn't seem like there's any hope to sort of understand what these critical gauges look like. Here, and here I did one for, but here, I did one for a large graph. I took like the big hexagon. This is my downstairs graph. Let's see. When you find the critical gauge, right? I started with all the edge weights, all the edge directions, all the edge weights 1, and I look for the critical gauge. At each vertex, it has 3 adjacent edges. Let's call the horizontal one x, this one y, and that one z. Then I can map that vertex into the triangle, because x plus y plus z equals 1, I can map it into the plane x plus y plus z equals 1, and everything is positive, so I'm inside that positive triangle. Or if you like, I'm just mapping into the very central coordinates in your triangle. And what you find is that something cool happens, which is that here, this is not the image of this one. I took it like a hexagon with side 20 or 25, I forgot, and I mapped that one in. And so each vertex here is the image of one of the vertices here. This is an image of this hexagon mapped inside the triangle, and it maps twice around. It's a branched over somewhere near the center, but it has there's obviously something going on with this critical gauge function. It's sort of converging to some smooth function. And the goal, I want to tell you how to find that function, or at least approximate that function. Did everybody understand what's going on? Right? It's a very simple problem, which, this problem of finding a gauge where the adjacency matrix becomes bistochastic is something that people have studied for a long time in the mass transport and in statistics. You're making contingency tables. And there are various algorithms. Like there's one algorithm which is called Sinkhorn crop algorithm, where you just solve for the x's on the right first, and then you solve for the x's on the left. First, you make the row sums equal to 1, then you make the column sums equal to 1, and then you repeat over and over again. This will converge exponentially quickly to the actual solution. So it's not that, we didn't invent that algorithm, it's just we applied it in this particular setting. And so that's how I made this picture. It converges very quickly. Okay, so then you tried for another graph. Here's another graph that you might be familiar with, Aztec Diamond graph. And the critical gauge in this case comes out to be curiously simple. It's just, it's actually a rational function on the vertices, kind of a linear function of the two coordinates. You can see sort of 1/5, 2/5, 3/5, 4/5, for mysterious reasons which we don't at all understand. The Aztec Diamond, the critical gauge has this nice simple rational form. And because it's so simple, you can say things about it in the scaling limit. Let's take a very large one. If I take a very large Aztec Diamond, so what are these numbers? These are the probability that this 1/5 here, that's the probability that edge gets, that's the fraction of dimers which project to that edge. And so, there's an associate in this multivariable, multinomial dimer model, there's a height function, just like in this single dimer model. And if you look at the height function in the scaling limit, it becomes this very nice, has the same boundary conditions as the usual Aztec Diamond, sort of linear, piecewise linear around the boundary. But here the solution is very simple. It's just x squared minus y squared. Nice harmonic function. The harmonic function extending those boundary conditions. So, however, the answer is it's not always a harmonic function. This is just a particularly simple case. But there is a certain PDE that the height function satisfies, which happens to be satisfied by this one in this particular situation. So this kind of the mystery here is that for some reason for the Aztec Diamond, the critical gauge is rational, but not looking to gift horse in the mouth here. We're just going to go with that, and we get the solution here. Okay, and there's an associated variational principle here. Just like in the standard dimer case, you take a region in the plane, say, you take let epsilon be very small, and you take an approximation of the region by a discrete graph inside, well, I should have said epsilon z squared here. I just rotated z squared because it's convenient to use these rotated coordinates. And then, if I have this large graph, right? How do I describe the critical gauge, and how do I describe the limiting height function, just like we did in the previous slide? We might not be so lucky to find an explicit formula for the critical gauge. What do we do? And the answer is that well, there's two ways to go about it. One is to look for the equation that the critical gauge will satisfy, and the other one is there's some sort of, because it is a critical gauge, there's some variational principle that it satisfies. And likewise, the height function also has a variational principle associated to it, just like the single dimer model. And so that's let me explain how it works in the gauge first, and then I'll explain how it works in the height function, and then I'll show that they're connected, and then we'll do the higher dimensional case. So, suppose let's go back to our Z2 graph, right? And we're looking for a critical gauge. What does that mean? I'm looking for a function on the white vertices, f, let's call it f. On the white vertices, another function on the black vertices, g. And it has to satisfy this, right, around each, at each black vertex sitting at xy, right? I got the value there is g, and the value over here at x plus 1y, that's a white vertex. Blackboard white. And so along this edge, the edge weight is just the product of these two values. And then I want the sum of the edge weights to be 1 there. That's that first equation. And the second equation is the same at a white vertex. So I have to satisfy this kind of nonlinear recurrence difference equation for on my region. But we can here's the sort of recipe for doing that. Let me change coordinates by, first I want to scale my lattice by epsilon and rotate the coordinates by 45 degrees. So let's let x be, I plus j over 2 times epsilon, y be I minus j over 2 times epsilon, and then let's call our rotated function capital F. Then this, if you look at this equation, little f is the same as big F. I divide by little f, and then each g here I replace by 1 over the sum of the 4 f's from the previous equation. So it looks kind of like this. You get this kind of nasty looking large difference equation. I just eliminated g from these equations, and 1 became epsilon because I scaled my lattice. But then you can just use a Taylor series of this for both sides of this equation. And so if I write f as e to the 1 over epsilon times h, and you have to justify this form of the solution where h is smooth, then just Taylor series both sides, you find this PDE for h. And that's the PDE which describes the critical gauge function. You can kind of see that, when you expand this to order epsilon squared, the leading terms all cancel. This one is roughly 1 over 4f. Each of these terms is 1 over 4f. So when you sum, the leading terms cancel, and the terms of order epsilon cancel by symmetry, by the symmetry, and then so the epsilon squared term is the term which gives you this equation. And anyway, and the claim is that if you solve that equation, then the actual critical gauge on the graph will lie close to that, and that requires some proof. But we get that proof in the paper. This is a sort of a nonlinear PDE for the function capital H, which describes the critical gauge function on the black, and similarly for the white vertex. No, okay, well, yeah, okay. The order got a little turned around, but you can do the same thing in terms of the height function. And here's the statement, which combines both of those things. So on a region like this, you have a domain R in the plane, has a certain boundary height function. The actual limiting height function for the multinomial dimer model has a variational principal. Satisfies a variational principal, you maximize the entropy, which is a local surface tension integral. Surface tension only depends on the gradient of the height function, and the surface tension formula turns out to be fairly simple. It's just a sum of Shannon entropies of the x and y derivatives of the height function, S and T. If you're familiar with the dimer model, it looks very similar. Up to here, it's just the form of sigma is different. This sigma, is a much more tame function. It only involves logarithms rather than sort of dilogarithms in the dimer model. And from this variational principle, you can find the Euler-Lagrange equation for the limiting height function, and it looks and here it is, in terms of the height function, it's just some variant, some sort of nonlinear Laplacian equation, hxx over 1 minus hx squared, over 1 minus hy squared. Also looks a little bit like a minimal surface equation, except that there's no cross term. It's kind of like it's almost exactly the minimal surface equation without the cross term. Maybe there's a sign missing somewhere. Maybe for the minimal surface, this is a plus. But yeah, and if you formulate it in terms of the critical gauge, which I did on 2 slides ago, you get a very different looking equation, but these 2 equations are related to each other. They're dual in some sense. Our main theorem of this talk, which I haven't told you anything about, is that there's a similar statement which holds for much more general graphs, and in particular for graphs in Z3 or other lattices in R3. We didn't try to do it for higher dimensions, although I think in principle can be done. It's just that getting the variational principle, all the patchings, and to work out is a little bit painful already in 3 dimensions. But fortunately, there was work of Catherine with Scott and Nishant who worked out for the single dimer model in Z3 all the variational principle and patching stuff, and we could import that stuff and reprove it in this setting. Okay, well, what happens at the end of the day, you get a PDE, reasonably simple looking PDE, but solving nonlinear PDEs, even elliptic ones, there's not some general technique. But one thing that saved us in 3 dimensions is that we have some examples for which we have explicit critical gauges, and one of them is this sort of 3D Aztec diamond. So let me describe that example now. There are various versions of the 3D Aztec diamond, but this is the one which works for us. Instead of using the Z3 lattice, we're going to take the BCC lattice, the body centered cubic lattice. So if you look at the reds here, they form A by B by C box in Z cubed, and the blues are an A plus 1 by B minus 1 by C minus 1 box in the lattice, which is shifted by a half. So the vertices of the blue lattice lie in the centers of the cubes of the red lattice. So that's called the body-centered cubic lattice. And here A, B, C are just any integers, but if we want to have multinomial pilings, we need the number of red vertices to be equal to the number of blue vertices. And so you have to satisfy this condition, but it's not hard to arrange to find triples A, B, and C to satisfy that condition. And so the goal is to do the multinomial dimer model on this 3-dimensional version of the Aztec diamond. I guess maybe it's not obvious why that's the same as the Aztec diamond, but if you take that usual Aztec diamond and you rotate it 45 degrees, then it is indeed the union of all the black vertices form a rectangle and the white vertices form a rectangle, and the edges go diagonally like that. So hopefully that's convincing that this is some version of some 3D version of the Aztec diamond. So the amazing thing about this guy is that, again, there's an exact critical gauge, which is rational. And the critical gauge is given by, at red vertices, you just take this ratio of binomial coefficients, A choose I divided by B choose J, C choose K. And at the blue vertices, it's very similar, with B minus 1, C minus 1, A plus 1, times some constant. Again, very, very mysterious, reasons, we don't have a priori reason to expect that this phenomenon takes place, but it does.
You showed us the numbers for the critical gauge in the 2D case, but you didn't show us the formula. Does it?
Oh, it looks very similar. It's just ratios of binomial coefficients. It's in the paper. I can show you afterwards. But yeah, these are the values on the vertices, and then you multiply them to get the value on the edges. And when you multiply these binomial coefficients, there's some cancellation. So it's just
A equals 1 gives the Aztec, right?
if not exactly. Well, if A equals 1, then the blues still have 2 layers. Yeah, so it's a little bit slightly different. Anyway, so once you have the exact critical gauge, it's easy to get the the edge weights and by the way, in 3 dimensions, there's no height function. The analog of the height function is some sort of 2 form. But what you can do is describe your tiling with the vector field. I should have added a slide here. When you have a dimer cover, even in the plane, you can think of at each vertex there's some probability of going in any given direction. So you could think of a dimer cover as a sort of a random vector field, and in the large scale limit, the expectation of that vector field will have will be some smooth vector field. And in this case, the limiting vector field in this A by B, well, I rescaled, so let's call the 3 dimensions alpha, beta, and gamma, is this nice, well, it's a divergence free for combinatorial regions. It's a divergence free vector field, 2x over alpha minus 1, 1 minus 2y over beta, 1 minus 2z over gamma. And beautifully simple formula. I made a nice picture. I don't know, kind of hard to draw a 3-dimensional vector field, but what I did is I drew the integral curves of the vector field. The vector field sort of comes in on the large boundaries and goes out on this is like a 2 by 2 by 1 box. I think this is alpha equals 1, beta equals 1, gamma equals 2 or something. Yeah, 1, 2, and 2. And then it comes in on the large sides and goes out around the perimeter, and it's divergence free. So that is the 3D limit shape you get from this multinomial Aztec diamond. And there are no facets. There are no facets in this model. The limit shape is always analytic. Yeah.
So do the edge weights somehow satisfy the tetrahedron equation? 3D version of Yang-Baxter?
No, there doesn't seem to be any sort of Yang-Baxter-ish phenomenon here in this model. Yeah, we're not doing the dimer. We're not doing the dimer model. There's no cluster structure as far as we know. But we do have there's some mysterious integrability. I mean, in the simplest sense of the word, right? In integers, right? But if you want to write down the PDE, there's a PDE for the gauge, and it's also reasonably simple. In this case, how do you solve such a thing? I have no idea. Right? In general, if I have more general boundary conditions or more general region, we have no idea how to solve it. Unlike the 2-dimensional case where there are some techniques for solving these kind of PDEs, you find the invariant conformal structure and so on. Here, there's nothing like that. But there's a duality between the vector field and the gauge, just like in the previous case. I don't know, this slide is not very informative, but there's a PDE for H, there's a PDE for the vector field, and there's there's 3 equations for the vector field plus the divergence-free condition. The vector field is described by 3 functions, u, v, and w, because there's 3 coordinates. And then the y derivative of u is the x derivative of v divided by these things. And the kind of cool thing which we learned, which apparently not very many people know, is that the duality connects the the Euler-Lagrange equation for the vector field with the mixed partial equations for the gauge. And conversely, the PDE for the Euler-Lagrange equation for the gauge corresponds to the divergence-free condition for the vector field. It's kind of a weird kind of duality, which we learned about. Yeah, so we spent some time looking around for other graphs for which the gauge had the nice rational form, and we mostly struck out. But here's an example, which we could do. It's another three-dimensional example. It's kind of hard to tell what's going on here, but it's what you do is you take the positive orthant, and then you truncate it by a plane x plus y plus z equals n. And then inside that, so now it's an infinite graph, and you put this sort of diamond lattice dimer model, which is some version of the 3D honeycomb dimer model, if you like, diamond lattice dimer model. And there we could find a critical gauge as well, which happened to be rational, have rational edge weights. Right, I didn't write them down, but there's trinomial coefficients this time rather than binomial. Ratios of trinomial coefficients. There's some nice criticality equation, if you care, for the gauge function, which doesn't really help. But because we have an explicit gauge, we can find the scaling limit vector field, which has this nice rational form. And you can check that that's divergence free. Finally, you can ask about fluctuations, right? The Euler-Lagrange equation gives you the sort of law of large numbers, the concentration of the measure, but you can ask how the fluctuations of the edge multiplicities away from their expectation. And the general theory of the multinomial model gives you some way to shows that those fluctuations are typically Gaussian, unless something very special happens. And they are Gaussian in this case, but they're described by some Gaussian field, which is a little bit unusual, I guess. It's an inhomogeneous Gaussian free field. So what I did was, this is just the Aztec Diamond again. I took the Aztec Diamond, rotated by 45 degrees, so it's in a square. In scaling limit, the height fluctuations, let me just talk about the height fluctuations. Well, that's really all there is in this case. They're given by the image of a certain inhomogeneous Gaussian free field on there. Yeah, here's the Aztec Diamond. Here's the domain. So you start with a standard Gaussian free field on this domain with a standard conformal structure, but an unusual Laplacian, where the Laplacian has a varying conductance. It's like taking the Laplacian on a copper plate, where the copper plate has a thickness which gets thinner and thinner near the boundary, and the conductance is as a function of u and v looks like this: 1 over sine u sine v. So the conductance, I said it wrong. The conductance, the plate gets thicker and thicker near the boundary because the conductance blows out near the boundary. And so you take the Laplacian with respect to that conductance function, which looks like this, and you take its Gaussian free field, and use the standard conformal structure here. That's illustrated by these little circles. Then you apply this diffeomorphism from that square to this square, which is just given by that map there. So the conformal structure is degenerating near the boundary, and also the Gaussian free field is sort of getting stiffer near the boundary. So this is a Gaussian free field where it's sort of the stiffness of the Gaussian free field is going to 0 here. The variance is going to 0 near the boundary. As the conductance goes up, the stiffness gets stronger, stiffer. The stiffness gets higher. Imagine, or if you like, imagine a sort of a set of springs where the spring constant, you have your bed, and the spring constant gets thicker and thicker near the boundary, so that the the boundary is sort of pinned to the frame of the mattress in a very strong way. The spring
It's kind of like
constants are very-
trying to freeze,
What?
but not quite. It's like trying to freeze, but not quite freezing in some
That's,
sense.
yeah, it's kind of like that, yeah. It's like, the spring constant, the stiffness is going to infinity near the boundary. Anyway, then you take the image of that, and that is the Aztec Diamond fluctuation scaling limit Gaussian field. Well, I don't have time to explain, where this comes from, but there's a very general setup for other multinomial tiling models, even non-dimer models, which always gives you a Gaussian fluctuations, and this is the answer in this particular setting. I think that's all I had to say. Thank you.
Questions for Rick? Yeah, go ahead.
So I have two questions. One is, when you have these edge probabilities for the Aztec Diamond, is there any kind of relation or recurrence for Aztec of size n plus one versus size n? I'm guessing it seemed like there should be a shuffling algorithm, but is there like a precise relation between these for different n?
Not that we could find. I mean, well, in the sense that 1/5 and 1/6 are related to each other. You invert from that, and each, if you go along each row, it's a linear function. So in some sense, you could invent a relation, but I don't see any sort of reason for that relation to hold a priori. I think that was your question.
Yeah. Okay. Thanks.
Yeah. The usual Aztec Diamond, there's this nice shuffling stuff, but as far as we know, there's no analog here.
And then my other question is, you have these two examples, the 3D hexagonal lattice, the 3D Aztec Diamond. How did you find them? And did you find any others?
Yeah, we found a few others, but our list is embarrassingly short. So if you have some, and I can't really tell you how I found them. Really what I did was, how do I find a critical gauge? Let me try some graphs. Let's try the Aztec Diamond, and I did it numerically, and I saw, well, 0.2000. That looks like 1/5. And then I figured, did the rest of them, and I saw that the damn thing converged to some rational numbers. That's how I discovered it. Another graph we tried very recently was the domain wall boundary 6 vertex model in domain wall boundary conditions. If you take a uniform measure, then it's not a dimer model, but it is a multinomial. You can take the multinomial version of that, and that also has a nice rational critical gauge. But for what it's worth, I don't have any theory that would lead to more examples. I think we can do this one in all dimensions now. Just it always ends up to be some ratio of binomial or binomial coefficients, but that's about as far as we got. Yeah.
That diffeomorphism you had on the last slide.
Yep.
Is that so how exactly is that related to those critical gauges? Is that like some other critical gauge itself in some sense, or
This one. Oops.
yes?
I don't remember what the critical. Well,
Or maybe my question is like, how do you get that diffeomorphism?
okay, yeah. There's a story. There's an interesting story. Yeah, it's kind of an advertisement for previous paper I worked on with Istvan Kraus, where when you have a two-dimensional variational problem like that one, like the one we have here, this one, where the surface tension only depends on the gradient, then you can look for an invariant conformal structure. And when you write the equation in that conformal structure, nice things happen. The equation becomes linear and so on. You can solve, there's just lots of techniques. And so if you write everything in that conformal structure, then the equation separates, the x and y variables separate, and it's easy to sort of solve the equation. So but you wouldn't expect that to be so simple in a more general case. for more general regions. But the moral of that Kenyon Browse paper is that you should always look for the invariant conformal structure in any such variational problem, at least in 2 dimensions, because it's always the right coordinate to work in.
Any further questions? Okay, let's not come back.